Bismillah, welcome to Think Math. Today we study continuity. Intuitively, a graph is continuous when there is no break, hole, or jump at the point we are studying. A common informal description says that we can draw the graph without lifting the pen. In this lesson, we will study continuity at a point, continuity on intervals, the main types of discontinuity, and several worked examples. Before continuity, let's quickly review one-sided limits. The left-hand limit, written as limit x tends to a from the left, describes the value approached from values smaller than a. The right-hand limit, written as limit x tends to a from the right, describes the value approached from values greater than a. The two-sided limit exists if and only if the left-hand limit equals the right-hand limit. A function f is continuous at x equals a if three conditions hold together. First, the function value f of a must exist. Second, the limit of f of x as x approaches a must exist. Third, the limit must equal the actual function value. If even one condition fails, then the function is not continuous at that point. Now, let us classify the main types of discontinuity. A removable discontinuity occurs when the limit exists, but the function value is missing or incorrect. So, one point can be fixed. A jump discontinuity occurs when the left hand and right hand limits both exist, but they are not equal. An infinite discontinuity occurs when the function grows without bound near the point, usually around the vertical asymptote. A function is continuous on the open interval a to b if it is continuous at every point inside the interval. On the closed interval from a to b, we also check the endpoints. The function must be right continuous at a and left continuous at b. On an open interval, continuity means continuity at every interior point. On a closed interval, the endpoints must also be checked. We use right continuity at a and left continuity at b. Let us recall some common continuous functions. Every polynomial is continuous on all real numbers. Every rational function is continuous wherever its denominator is not zero. The sine and cosine functions are continuous on all real numbers. The tangent function is continuous wherever it is defined, except at pi over 2 plus n pi. Let's take some examples. In the first example, we study the function 2x squared minus 7x minus 4 over x minus 4 at x equals 4. We factor the numerator as 2x plus 1 times x minus 4, so for x not equal to 4, the function becomes 2x plus 1. Therefore, the limit as x approaches 4 is 9, but the function is undefined at x equals 4, so it is not continuous there. This is a removable discontinuity, and defining f of 4 to be 9 makes the function continuous. In the second example, we study a piecewise function at x equals 2. We have f of x equals 2x plus 3 when x is greater than 2, and 5x minus 3 when x is less than 2. We are required to get the continuity of the function at x equals 2. Now let us see a true jump discontinuity with a non-constant example. Consider g of x equals x plus 2 for x less than 0, and x squared plus 1 for x greater than or equal to 0. As x approaches 0 from the left, the function approaches 2. As x approaches 0 from the right, the function approaches 1. Since these two one-sided limits are different, the two-sided limit does not exist. Therefore, the function has a jump discontinuity at 0, and this kind of discontinuity cannot be removed by redefining one point. In the next example, the function equals x to the power of 7 minus 128 over x to the power of 4 minus 16 when x is not equal to 2, and it equals 44 at x equals 2. To test continuity, we compute the limit at 2. Both numerator and denominator vanish. We use the corollary we explained in a previous video. The limit as x approaches a of x to the n minus a to the n, divided by x to the m minus a to the m. equals n over m times a to the power n minus m. After substitution, the limit equals 14. But the function value is 44, not 14. Therefore, the function is not continuous at 2. Since the limit exists, the discontinuity is removable, and redefining the function value to 14 makes it continuous. The next example, the function is given with two unknown constants a and b. We are told the function is continuous at x equals 2, and we must find the value of a and b. So f of x equals x squared plus ax minus 2 when x is greater than 2. The function is equal to 4 when x is equal to 2. And f of x equals 5a plus bx when x is less than 2. And from the right-hand limit, 5 squared plus 2a minus 2 equals 4, so a equals 1. From the left-hand limit, 5a plus 2b equals 4, then 5 times 1 plus 2b equals 4, then b equals negative half. Then a equals 1 and b equals negative half. Next, we study a trigonometric piecewise function. Each branch is continuous on its own interval, so we only need to check the joining point x equals pi. We have f of x equals sine x minus cosine x when x is greater than or equal to 0 and less than or equal to pi, and f of x equals 2 cosine squared x minus 1 when x is greater than pi. So f of pi equals sine pi minus cosine pi equals 1, and the limit when x approaches pi from greater values equals 2 cosine squared pi minus 1, which is equal to 1, and the limit when x approaches pi from the lower values equals sine pi minus cosine pi, which is equal to 1. From the left branch, f of pi is 1. From the right branch, the limit is also 1. Since the left-hand limit, the right-hand limit, and the function value are all equal, the function is continuous at pi. Now, try these exercises. First, discuss the continuity of the rational function x minus 4 over x squared minus 5x plus 6 on the real numbers. Second, determine a and b so that the three-part piecewise function is continuous on all real numbers. Use the same idea in every example, check the function value, check the limit, and compare them carefully. Let's quickly review the answers to last lesson's quiz. Thank you for watching. See you in the next lesson.